What is clustering? So we'll have a group of people here hanging out at a table or local coffee shop. I'm guessing coffee shop since they all have the same mugs. And one of them is trying to figure out what they're going to do. I have 20 places to cover in 4 days. I guess he's going traveling. That sounds fun. One of those breeze through Costa Rica or visiting the US or going to Europe to go visit all the highlights. So he's got 20 places he wants to go and he wants to hit them in 4 days. Very ambitious. And how will I manage to cover all of them? That's the question that he's coming up. How am I going to get to all these different places in the short time I have? Maybe he's a sales team, so he has 20 places he's got to do demos for. You can make use of clustering by grouping the places into 4 clusters. Each of these clusters will have places which are close by. So we're going to cluster them together by what is closest to the other one. Then each day you can visit one cluster and cover all the places in the cluster. Great! That's a great idea. If you're going to hit 4 different places, maybe you're going to cluster whatever streets are closest together so you don't have to travel, spend all your time traveling. The method of dividing the objects into clusters, which are similar between them and are dissimilar to the objects belonging to another cluster. So this is a formal definition of clustering. And we have here what we call hierarchical clustering and partial clustering. And we're going to go more into detail on hierarchical clustering. And you'll see the difference between the two where partial clustering doesn't have the descending graph. It just has groups of things. And under hierarchical clustering, we're going to go over agglomerative and divisive. And you can think of agglomerative of bringing things together and divisive as dividing them apart. And then partial clustering, the 2 most common ones are k-means. That's probably the most common used for partial clustering. And there's also fuzzy c-means. And there's other ways of clustering and other algorithms out there. But these are the 2 big ones, k-means really being the most common one used. But we're not going to dig too deep into partial clustering because we're studying hierarchical clustering today. So what is clustering? Well, the applications of clustering are pretty numerous. We have things like customer segmentation, what people kind of belong together, how do we group them together? We have social network analysis. So social networks, we might look at sentiments. What group of people like something? What group of people don't like something? And then we can use that sentiments to suggest new sales for them. This whole group is into Harley-Davidson motorcycles, so we cater to them to sell them Harley-Davidson motorcycle parts. And we find out that people in that group also like leather jackets, they also like motorcycle boots, and they like bandanas. My brother's into Harley-Davidson, so that's why I picked that kind of funny example. But you can kind of see we look for similarities between these people, and then we group them together accordingly. And that's a good sentimental clustering is very common in so many things today, where we want to know the sentiments on stocks. Who is interested in stocks, who's not. Sentimental analysis, we talked about customer segmentation and sales. Well, we want to know what kind of sentimental view people have on different restaurants if we're going to open up a new restaurant or a new putting stores in. And of course, city planning. A lot of this I just kind of aimed at the city planning side. City planning is big with clustering. We want to cluster things together so that they work. We don't want to put an industrial zone in the middle of somebody's neighborhood where they're not going to enjoy it, or have a commercial zone right in the middle of the industrial zone where no one's going to want to go next to a factory to go eat a high-end meal or dinner. So it's very big in city planning. But it's also very big in just pre-processing data into other models. So when we're exploring data, being able to cluster things together, reveal things in the data we never thought about. And then once we have it clustered, we can put that into another model to help us figure out what it is we want for our solution. So let's go a little deeper into hierarchical clustering. Let's consider we have a set of cars and we have a group similar. We want to group similar ones together. So below we have, you'll see 4 different cars down there. And we get 2 clusters of car types, sedan and SUV. So if you're just looking at it, you can probably think, oh yeah, we'll put the sedans together and the SUVs together. And then at last we can group everything into one cluster. So we just have just cars. So you can see as we have this, we make a nice little tree. This is very common when you see anybody talks about hierarchical clustering. This is usually what you see and what comes out of it. We terminate when we are left with only one cluster. So we have, as you can see, we bring them all together. We have one cluster. We can't bring it together anymore because they're all together. Hierarchical clustering is separating data into different groups based on some measure of similarity. So we have to find a way to measure what makes them alike and what makes them different. Agglomerative clustering is known as a bottom-up approach. Remember I said think of that as bringing things together? You see, I think the Latin term Agglo is together because you have your agglomerate rocks where all the different pieces of rocks are in there. So we want to bring everything together. That's a bottom up. And then divisive is we're going to go from the top down. So we take one huge cluster and we start dividing it up into 2 clusters, into 3, 4, 5, and so on. Digging even deeper into how hierarchical clustering works, let's consider we have a few points on a plane. So this plane is 2D, so we have an XY coordinates, kind of makes it easy. We're going to start with measure the distance. So we want to figure a way to compute the distance between each point. Each data point is a cluster of its own. Remember, if we're going from the bottom up, agglomerative, then we have each point being its own cluster. We try to find the least distance between 2 data points to form a cluster. And then once we find those with the least distance between them, we start grouping them together. So we start forming clusters of multiple points. This is represented in a tree-like structure called Dendogram. So this is another key word, Dendogram. And you can see it's just the branch that we've looked at before. And we do the second group the same, so it gets its own dendogram, and the third gets its own dendogram. And then we might group 2 groups together. So now those 2 groups are all under one dendogram because they're closer together than the P1 and P2. And then we terminate when we are left with one cluster. So we finally bring it all together. You can see on the right how we've come up all the way up to the top. Whoops. And we have the gray hierarchical box coming in there and connecting them. So we have just one cluster, and that's a good place to terminate because there is no way we can bring them together any further. So how do we measure the distance between the data points? I mean, this is really where it starts getting interesting. Up until now, you can kind of eyeball it and say, hey, these look together. But when you have thousands of data points, how are we going to measure those distances? And there is a lot of ways to get the distance measure. So let's go ahead and take a look at that. Distance measures will determine the similarity between 2 elements, and it will influence the shape of the clusters. And we have Euclidean distance measure, we have squared Euclidean distance measure, which is almost the same thing but with less computations. And we have the Manhattan distance measure, which will give you slightly different results. And we have the cosine distance measure, which again is very similar to the Euclidean, playing with triangles. And sometimes it can compute faster depending on what kind of data you're looking at. So let's start with the Euclidean distance measure. The most common is we want to know the distance between the 2 points. So if we have point P and point Q, the Euclidean distance is the ordinary straight line. It is the distance between the 2 points in Euclidean space. And you should recognize D equals, in this case we're going to sum all the points. So if there was more than 1 point, we could figure out the distance to the not more than 1 points. This is the sum of more than 2 dimensions. So we can have the distance between each of the different dimensions squared, and that will give us, and then take the square root of that, and that gives us the actual distance between them. And this should look familiar from Euclidean geometry. Maybe you haven't played too much with multiple dimensions, so the summation symbol might not look familiar to you. But it's pretty straightforward as you add the distance between each of the 2 different points squared. So if your y difference was 2 minus 1 squared would be 2, and then you take the difference between the x, again squared, and if there was a z coordinates, it would be z1 minus z2 squared, and then take the square root of that and sum it all together and then take the square root of it. So to make it compute faster, since the difference in distances, whether one is farther apart or closer together than the other, we can do what's called the squared Euclidean distance measurement. This is identical to the Euclidean measurement, but we don't take the square root at the end. There's no reason to. It certainly gives us the exact distance, but as far as doing calculations as to which one's bigger or smaller than the other one, it won't make a difference. So we'll just go with so we just get rid of that final square root. It computes faster, and it gives us pretty much the Euclidean squared distance on there. Now, the Manhattan distance measurement is the simple sum of horizontal and vertical components, or the distance between 2 points measured along axes at right angles. Now this is different because you're not looking at the direct line between them. And in certain cases, the individual distances measured will give you a better result. Now generally that's not true. Most times you go with the Euclidean squared method because that's very fast and easy to see. But the Manhattan distance is you measure just the y value and you take the absolute value of it, and you measure just the x difference and you take the absolute value of it, and just the z. And if you had more, different dimensions in there, A, B, C, D, E, F, however many dimensions, you would just take the absolute value of the difference of those dimensions. And then we have the cosine distance. Similarity measures the angle between the 2 vectors. And as you can see, as the 2 vectors get further and further apart, the cosine distance gets larger. So it's another way to measure the distance. Very similar to the Euclidean, so you're still looking at the same kind of measurement, so it should have a similar result as the first two. But keep in mind the Manhattan will have a very different result, and you can end up with a bias with the Manhattan if your data is very skewed, if one set of values is very large and another set of values is very small. But that's a little bit beyond the scope of this. It's just important to know that about the Manhattan distance. So let's dig into the agglomerative clustering. And agglomerative clustering begins with each element as a separate cluster, and then we merge them into a larger cluster. How do we represent a cluster of more than one point? So we're going to kind of mix the distance together with the actual agglomerative and see what that looks like. And we're actually going to have three key questions that are going to be answered here. So how do we represent a cluster of more than one point? So we want to look at the math, what it looks like mathematically and geometrically. How do we determine the nearness of clusters? When to stop combining clusters? Always important to have your computer script or your whatever you're working on have a termination point so it's not going on eternally. We've all done that if you do any kind of computer programming or writing a script. Let's assume that we have 6 data points in a Euclidean space. So again, we're dealing with x, y, and z. In this case, just x and y. So how do we represent a cluster of more than one point? Let's take a look at that. And first we're going to make use of centroids. Very common terminology in a lot of machine learning languages when we're grouping things together. So we're going to make use of centroids, which is the average of its points. And you can see here we're going to take the 1, 2 and the 2, 1, and we're going to group them together because they're close. And if we were looking at all the points, we'd look for those that are closest and start with those. And we're going to take those two and we're going to compute a point in the middle. And we'll give that point 1.5, 1.5. And that's going to be the centroid of those 2 points. And next we start measuring like another group of points. We got 4, 1, 5, 0. When they're pretty close together. So we'll go ahead and set up a centroid of those 2 points. In this case it would be the 4.5 and 0.5 would be the measurements on those 2 points. And once we have the centroid of the 2 groups, we find out that the next closest point to a centroid is over on the left. And so we're going to take this and say, oh, 0, 0 is closest to the 1.5, 1.5 centroid. So let's go ahead and group that together. And we compute a new centroid based on those 3 points. So now we have a centroid of 1.1 or 1, 1. And then we also do this again with the last point, the 5, 3, and it computes into the first group. And you can see our dendogram on the right is growing. So we have each of these points become connected and we start grouping them together. And finally we get a centroid of that group too. And then finally the last thing we want to do is combine the 2 groups by their centroids. And you can see here we end up with one large group and it'll have its own centroid, although usually they don't compute the last centroid, we just put them all together. So when do we stop combining clusters? Well, hopefully it's pretty obvious to you. In this case when they all got to be 1, but there are actually many approaches to it. So first, pick a number of clusters k up front. And this is done in the fact that we don't want to look at 200 in clusters. We only want to look at the top 5 clusters or something like that. So we decide the number of clusters required in the beginning and we terminate when we reach the value k. So if you looked back on our clustering, let me just go back a couple screens. You'll see how we clustered these all together, and we might want just the 2 clusters. And so we look at just the top 2. Or maybe we only want 3 clusters. And so we would compute which one of these has a wider spread to it or something like that. There's other computations to know how to connect them. And we'll look at that in just a minute. But to note that when we pick the k value, we want to limit the information that's coming in. So that can be very important, especially if you're feeding it into another algorithm that requires 3 values, or you set it to 4 values, and you need to know that value coming in. So we might take the clustering and say, okay, only 3 clusters. That's all we want for k. So the possible challenges, this only makes sense when we know the data well. So when you're clustering with k clusters, you might already know that domain and know that that makes sense. But if you're exploring brand new data, you might have no idea how many clusters you really need to explore that data with. Let's consider the value of k to be 2. So in this case, in our previous example, we stop when we are left with 2 clusters. And you can see here that this is where they came together the best while still keeping separate the data. The second approach is stop when the next merge would create a cluster with low cohesion. So we keep clustering till the next merge of clusters creates a bad cluster low cohesion setup on there. That means the point is so close to being between two clusters, it doesn't make sense to bring them together. But how is cohesion defined? Oh, let's dig a little deeper into cohesion. The diameter of a cluster. So we're looking at the actual diameter of our cluster, and the diameter is the maximum distance between any pair of points in the cluster. We terminate when the diameter of a new cluster exceeds the threshold. So as that diameter gets bigger and bigger, we don't want the two circles or clusters to overlap. And we have radius of a cluster. Radius is the maximum distance of a point from centroid. We terminate when the radius of a new cluster exceeds the threshold. Again, we don't want things to overlap, so when it crosses that threshold and is overlapping with other data, we stop. So let's look at divisive clustering. Remember, we went from the bottom up, now we want to go from the top down. Divisive clustering approach begins with a whole set and proceeds to divide it into smaller clusters. So we start with a single cluster composed of all the data points. We split it into different clusters. This can be done using monothetic divisive methods. What is a monothetic divisive method? And we'll go backwards and let's consider the example we took in the agglomerative clustering to understand this. So we consider a space with 6 points in it, just like we did before, same points we had before. And we name each point in the cluster. So we have, in this case, we just gave it a letter value, A, B, C, D, E, F. Since we follow top-down approach in divisive clustering, obtain all possible splits into two columns. So we want to know where you could split it here. And we could do like a AB split and a CDEF split. We could do BCE, ADF, and you can see this starts generating a huge amount of data. ABCDEF. And so for each split, we can compute cluster sum of squares. And we can see here, actually have the formula out for us, BJ12 equals N1 of absolute value of x minus absolute value of x squared. So again, we're computing all the different distances in there squared, back to your kind of Euclidean distances on that. And so we can actually compute B of j between clusters 1 and 2. And we have the mean of the cluster and the grand mean, depending on the number of members in the cluster. And we select the cluster with the largest sum of squares. Let's assume that the sum of squared distance is largest for the third split we had up above, and that's where we split the ABC out. And if we split the ABC out, we're left with the DEF on the other side. We again find the sum of squared distances and split it into clusters. So we go from ABC, we might find that the A splits into BC and D into EF. And again, you start to see that hierarchical dendogram coming down as we start splitting everything apart. And finally, we might have A splits in B and C, and then each one gets their own DEF. And it continues to divide until we get little nodes at the end and every data has its own point. Or until we get to K, if we have set a K value. So we've kind of learned a little bit about the background and some of the math in hierarchical clustering. Let's go ahead and dive into a demo. And our demo today is going to be, for the problem statement, we're going to look at U.S. oil. So a U.S. oil organization needs to know its cells in various states in U.S. and cluster the states based on the cells. So what are the steps involved in setting this problem up? So the steps we're going to look at, and this is really useful for just about any processing of data, although I believe we're going to be doing this in R today. We're going to import the data set. So we'll explore our data a little bit there. Create a scatter plot. It's always good to have a visual if you can. So once you have a visual, you can know if you're really far off in the model you choose to cluster the data in or how many splits you need. And then we're going to normalize the data. So we're going to fix the data up so it processes correctly. We'll talk more detail about normalization when we get there. And then calculate the Euclidean distance. And finally, we'll create our dendogram so it looks nice and pretty and we have something we can show to our shareholders so that they have something to go on and know why they gave us all that money in salary for the year. So we go ahead and open up R, and we're actually using R Studio, which is really it has some nice features in it. It automatically sets up the 3 windows where we have our script file on the upper left, and then we can execute that script and it'll come down and put it into the console bottom left and execute it. And then we have our plots off to the right, and I've got it zoomed in, hopefully not too large a font but large enough that you can see it. And let's just go ahead and take a look at some of the script going in here. It's clustering analysis, and we're going to work, we'll call it my data, and we're going to assign it in R. This is a symbol for assigning. And we're going to go read CSV. Read CSV file. And we'll put that in brackets. And before we go any further, let's just look at the data outside of R. It's always nice to do if you can. And the file is going to be called utilities.csv. This would also be the time to get the full path, so you have the right path to your file. And remember that you can always post in the comments down below. And when you post down there, just let us know you want to connect up with Simplilearn so that they can get you this file, so you can get the same file we're working on and you can repeat it and see how this works. This is utilities.csv. It's a comma-separated variable file, so it's pretty straightforward. And you can see here they have the city, fixed charge, and a number of different features to the data. And so we have our ROR, cost, load, demand, cells, nuclear fuel cost on here. And then going down the other side, we have U.S. cities, Arizona, Boston. They have central U.S., so I guess they're grouping a number of areas together. The Commonwealth area, you can see down here, Nevada, New England, northern U.S., Oklahoma, the Pacific region, and so on. So we have a nice little chart of different data they brought in. And so I'm going to take that complete path that ends in the utilities.csv, and we're going to import that file. Let me just enlarge this all the way. Oops, I had an extra set of brackets here somehow. Or maybe I missed a set of brackets. This can happen if you're not careful. You can get brackets on one side and not the other, or in this case, I got double brackets on each side. There we go. And then the magic hotkeys in this case are your Control-Enter, which will let me go ahead and run the script. And so I've now loaded the data, and as you can see, I went ahead and shrunk the plot since we're going to be looking at the window down below. And we can simply convert the data to a string. Now, all of us do this automatically the first time. We say, hey, just print it all out as a string. And then we get this huge mess of stuff that doesn't make a whole lot of sense. So, and you can see here they have, you can probably kind of pull it together as looking at it. But let's go ahead and just do the head. And we'll do the head of my data. There we go. And Control-Enter on that. And the head shows the first 5 rows. You'll see this in a lot of different scripts. In R, you type in head, and then in brackets you put your data. And it comes through and lists the first 5 rows, as you can see below. And it shows Arizona, Boston, Central, and it has the same columns we just looked at. So we have the fixed charge, the ROR, the cost, the load, the D demand. I'm not an expert in oil, so I'm not even sure what D demand is. Cells, I'm guessing nuclear, how much of it's supplied by nuclear, and the actual fuel cost. And then the different states that it's in or different areas. And one of the wonders of R is all these cool, easy to use tools that are so quick. So we'll do pairs. And pairs creates a nice graph. So let me go ahead and run this. Whoops. The reason it gave me an error is because I forgot to resize it. So let me bring my plot way out so we can see it. And let's run that again. And you'll see here that we have a nice graph of the different data and how it plots together, how the different points kind of come together. This is neat because if you look at this, I would look at this and say, hey, this is a great candidate for some kind of clustering. And the reason is when I look at any 2 pairs, let's go down to, say, cells and fuel cost towards the bottom right. And when you look at them where they cross over, you sort of see things how they group together, but it's a little confusing. You can't really pinpoint how they group together. You could probably look at these 2 and say, yeah, there's pretty good commonalities there. And if you look at any of the other pairs, you'll start seeing some patterns there also. And so we really want to know what are the patterns on all of them put together, not just any 2 of them, but the whole setup. Let me go ahead and shrink my this down for just a second, just a notch here. And let's create a scatter plot. Oops. And this is simply just use the term plot in brackets, and then which values do we want to plot. And if we remember when we looked at the data earlier, let me just go back this way. In this case, let's go ahead and compare just two values to see how they look. And we'll do fuel cost and cells, and it's in my data. So we got to let it know which 2 columns we're looking at next to each other. And it will open up our plot thing and then go ahead and execute that. And we can see on those close up of what we were just looking at in the pairs. And if I was eyeballing this, I would say, oh look, there's a kind of a cluster up here of 5 items, and this one is hard to tell which cluster it'd be with, but maybe it's 6. You go in the top one, and you have a middle cluster and a bottom cluster, maybe 2 different clusters. So you can sort of group them together, fuel cost and the cells, and see how they connect with each other. And again, that's only 2 different values we're looking at. So in the long run, we want to look at all of them. And then the people in the back, they sent me the script so we can go ahead and add labels. So with my data text, fuel cost cells, the labels equals city, position 4. These are numbers you can kind of play with till they look nice. And oops, again, I forgot to resize my plot. It doesn't like having it too small. And we'll run that. I mistyped something in here. Oh, I did a lowercase d and they did a capital D. There we go. So now we can go in here and do this with my data. And you can see, a little hard to see on my screen with all the different things in there. It plots the actual cities. So we can now see where all the cities are in connection with, in this case, fuel cost and cells. So we have a nice label to go with the graph. And then we can also go ahead and plot, in this case, let's do, the ROR, oops. And we'll do that also with the cells, and do my data. Remember to leave it lowercase this time. So when we plot those two, we'll come over here, and it's going to, I'm surprised it didn't give me an error. And then we'll also add in the with statement, so we put some nice labels in there. And it's going to be the same as before, except instead of doing the fuel cost cells, we want the R cells. And we'll execute that. Oops, and of course it gives me an error because I shrunk it down. So let's redo those 2 again. There we go. And we can see now we have the ROR with cells. And we'd probably get a slightly different clustering here if I was looking at these cities. They're probably different than what we had before. But you could probably look at this and say, these kind of go together and those kind of go together. But again, we're going to be looking at all of them instead of just 1 or 2. And so at this point, we want to dive into the next step. We're going to start looking at a little bit of coding or scripting here. This is very important because we're going to be looking at normalization. We put that in there, normalization. And if you've done any of the other machine learning skills and setup, this should start to look very normal in your pre-processing of data. Whether you're in R or Python or any of these scripts, we really want to make sure you normalize your data so it's not biased. Remember, we're dealing with distances, and if I have, let's say the ROR is, even look at this graph here on the right, you can see where my ROR varies between 8 and 14. That's a very small variable. And our cells varies between 4,000 and 16,000. So you can imagine the distance between 4,000 and 8,000, which is the distance of 4,000, versus 8 to 10 versus 2, the cells is going to dominate. So if we do any kind of special work on this, it's going to look at cells and it's going to cluster them just by the cells alone. And then ROR might have a little tiny effect of 2 versus 4,000. We want to level the playing field. Turns out there's actually a number of ways in script to normalize. So I'm just going to put in the code that they put together in the back for me. And let's talk about it a little bit. So we have Z, we're going to assign it to my data. And it's go ahead and we're going to do a little reshaping across all rows. Or across all columns. So each of the rows is going to have a little reshaping there. And then we're going to get M, which stands for means. And we're going to apply it to my data. So again, we want to go ahead and create the most common variable in there. And then S is going to be, SD stands for standard deviation. So instead of just doing, a lot of times what they do with normalization of data is we just reshape the data everything between 0 and 1. So that if the lower end is 8, that now becomes 0, and the upper end is 14, that now becomes 1. That doesn't help if it is not a linear set of data. So with this, we're going to look for the means and the standard deviation for reshaping the data. And that way the most common values now become the kind of like the center point. And then the standard deviation is how big the spread. So we want the standard deviation to be equal amongst all of them. And then finally we go ahead and take z, and with the z we're going to reassign it, and we're going to scale the original my data, which we reshaped, based on m and based on the standard deviation. And the 2 in here, that just means we're looking at everything in kind of a XY kind of plot. And we can quickly run these. Control Enter, Control Enter, Control Enter, Control Enter. So now we have Z, which is a scaled version of my data. And now we can go ahead and calculate the Euclidean distance. Oops, calcu. There we go. And in R, this is so easy. Once you've gotten to here, we've done all that pre-data processing. We'll call it distance. And we'll assign this to dist. So dist is the computation for getting the Euclidean distance. And we can just put z in there because we've already reformatted and scaled z to fit what we want. Let me go ahead and just hit enter on that. And I'm going to widen my left-hand side again. I'm always curious, what does this data look like? So let's just type in distance, which will print the variable down below. Oops. You have to hit Control Enter. And this prints out a huge amount of information. As you can see, it just kind of streams down there. And let's go ahead and enlarge this. And I don't know about you, but when I look at something like this, it doesn't mean a whole lot to me, other than I see 2, 3, 4, 5, 6, and then you kind of have the top part, 6, 17, 18. So imagine this is like a huge chart, is what we're looking at. And we can go ahead and use print, distance, digits equal 3. And let's run that. Oops, I keep forgetting that it has to go through the graph on the right. And we see a slightly different output in here. Let me just open this up so we can see what we're looking at. And by cutting down the distance, you can start to see the patterns here of it's looking at the different distances. So if I go to the top, we have the distance between 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, and then 2 and 3, and so on. Obviously, the distance between itself is 0, and it doesn't repeat the data, so we don't care to see 2 versus 1 again, because we already know the distance between 1 and 2. And so we have a nice view of all the distances in the chart, and that's what we're looking at right here. And it's a little easier to read. That's why we did the print statement up here to do digits equals 3. Make it a little bit smaller. We could even just do digits. Oh, let's just do 2. See what that looks like. We might lose some data on this one if something's way off. But we have a nice setup and we can see the different distances, and that's what we were computed here between each of the points. And then the whole reason we're doing this is to get ourselves a nice dendogram going, a nice clustering dendogram. We'll do a couple of these looking at different things. We'll take a variable hc.l and we're going to assign it h cluster and then distance. That easy. We've already computed the distances, so the h clustering does all the work for us. And let me hit enter on there. So now we have our HCL, which is assigned the h clustering computation based on distances and apart. And then I'm going to expand my graph because we would like to go ahead and see what this looks like. And we can simply plot that and hit the Control Enter so it runs. And look at that, we have a really nice clustering dendogram. Except when I look at it, the first thing I notice is it really shows like numbers down below. Now, if you were a shareholder and some data scientist came up to you and said, look at this is what it means, you'd be looking at that going, what the heck does 3, 9, 14, 19, 1, 18 mean? So let's give it some words there. So let's do the same plot with our HCL. There we go. And let's add in labels. And this is just one of the commands in plots. So we have labels equals my data. And then under my data, we want to know the city. And we'll have it hang -1. That's just the instructions to make it pretty. So we'll run that. Oops, I accidentally ran just hang my 1. Let me try that again. There we go. Okay, so now you can see what it's done. And the hang my 1 turns it sideways. That way we can see central, which is central US, and Kentucky. And we start to actually get some information off our clustering setup. And the information you start looking at is that when we put all the information together, you probably want to look at Central America and Kentucky together. Oklahoma and Texas has a lot of commonality, as does Arizona and southern US. And you could even group all 5 of those: Florida, Oklahoma, Texas, Arizona, and southern US. These regions, for some reason, share a lot of similarities. And so we want to start asking what those similarities are. But this gives us a place to look. It says, hey, these things really go together. You should be grouping these together as far as your cells and what you're doing. And then one of the things you might want to do is we can do the Dendogram average. And this changes how we do the clustering. So it looks very similar like we had before. And there's our HCl. We're going to assign it. We're going to do an H cluster. We're still doing it on distance. Oops, distance. And this time we're going to set the method to average. So we can change the methodology in which it computes the values. And before, if you remember correctly, we did median. Median's a little bit different than means. We did the most common one, and then we want the average of the median. And let's go ahead and run that. And then we can plot. And here's our HCl. Oops, there we go. Here's our HCl, and I can run that plot. And you can see that it's changed a little bit. So our way it computes and groups things looks a little different than it did before. And let's go ahead and put the cities back in there and do the hang. Control copy. Let me just real quickly copy that down here, because we want the same labels. And again, you can see Nevada, Idaho, Puget. I remember we were looking at southern US and Arizona, Texas and Oklahoma, Florida. So the grouping really hasn't changed too much. So we still have a very similar grouping. It's almost kind of flipped it as far as the distance based on average has. But this is something you could actually take to the shareholders and say, hey, look, these things are connected. And at which point you want to explore a little deeper as to why they're connected, because they're going to ask you, okay, how are they connected and why do we care? But that's a little bit beyond the actual scope of what we're working on today. But we are going to cover membership, what's called clustering membership on there. And let's create a member. We'll just call it member 1. Oops, there, member.1. And we're going to assign to this, we're going to do cut tree. And cut tree, it limits it. So what that means is I take my hc.l in here. Oops, there we go, .l. And so I'm taking the cluster I just built, and we want to take that cluster, and we want to limit it to just a depth of 3. So we go ahead and do that, and run that one. Oops, let me go run. There we go. So now I've created my member 1. And then, whoops, let me just move this out of the way. We're going to do an aggregate, and we're going to use Z, remember Z from above, and we're going to turn member 1 into a list, and then we're going to aggregate that together based on the mean. Let me go ahead and enter, run that. Oops, I did member L, it's actually member 1. There we go. And if we take a look at this, we now have our group 1 fixed charge, and then all your different columns listed there. And most of them should come up kind of looking between 0 and 1, but you'll see a lot of variation because we're varying it based on the means. So it's the means and standard deviation, not just forcing it in between 0 and 1, which is a much better way usually to normalize your data than just doing the 0-1 setup. And finally, we can actually look at the actual values, and the same chart we just did. Oops. I made a mistake on there with my data. There we go. Okay. And again, we now have our actual data. Instead of looking at just if you looked up here, it's all between 0 and 1. And when we look down here, we now have some actual connections and how far distance this different data is. Again, becomes more of a domain issue and understanding the oil company and what these different values means. And you can look at these as being the distances between different items. So a little bit different view, and you have to really dig deep into this data. What we really want you to take away from this is the Dendogram and the charts that we did earlier. And that is the cluster output and our nice Dendogram. So this would be stage 1 in data analysis of the cells. Again, you'd have to have a lot more domain experience to find out what all the individual numbers we looked at mean and what the distance is and what's difference between Central America and Kentucky and why they're similar and why it groups all of Central Kentucky, Florida, Oklahoma, Texas, Arizona, and Southern U.S. together into one larger group. So that'd be way beyond the scope of this. But you can see how we start to explore data and we start to see things in here where things are grouped together in ways we might not have seen before. And this is a good start for understanding and giving advice for sales and marketing, maybe logistics, city development. There's all kinds of things that kind of come together in the hierarchical clustering as you begin to explore data. And we just want to point out that we get 3 clusters of regions with the highest cells, region with average cells, region with the lowest cells. Again, those are some of the things that they clustered it around, and you could actually see where things are going on or lacking. In this case, if you're the lowest cells, no one wants to be in the region of the lowest cells.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.